Hello. Coming back. Hello. Hello.
Hey.
Very sorry about that. Rule number one, presenting test, we've got graphics drivers first. So, Ubuntu 16.04 does not work, sadly. There you go, that's what we found out. So all of the live coding I was going to do, I can no longer do, so sorry about that. We'll just have to talk through it. So, we work for a startup based in a small place near Barcelona, agricultural startup that helps farmers to manage fields, basically. So they sit on the tractor all day, because the tractors drive themselves now with GPS, and they're sitting on Facebook. It's true, no? It's unbelievable. The Facebook page of Agricultores de España has got how many members? Thousands. Yeah, 100,000 anyway, so it's pretty cool. And they put great pictures of the tractors on, they love their tractors. Anyway, talking seriously, farmers work really hard, and they have to spray their fields and, you know, put pesticides on, and what else do they put on? Fertilizer and all these things. They have to fill out forms in order to get subsidies to meet environmental standards, that not put too much poison on the fields, etc., etc. So this application helps them to basically click on a field and say, right, I sprayed this amount a day, and it all gets automatically made into a report. So that's basically what we do. I work for them part-time. I'm basically a database programmer. I'm not going to talk about Python at all, so you can all leave now. He's a full-stack web developer. He's going to talk about Python and Django, as you can see. Am I talking too fast? Because I am English. I do. No? Okay. So, the problem, sorry, our sides aren't nearly as slick as our predecessors. So, the problem we have is that we have these shape files. Some of them are very complicated. And covering all of Spain, there's 60 million of these files. It's called a format called Shape, which comes from a company called Esri. I'll go through that in a moment. And they're very big, and they're very unwieldy in a shape format. And the farmer's sitting there in the field, often in the middle of nowhere on a very slow connection. He just wants to see his field because they love maps. So basically, what we did is, actually I'll show you first how to come under F5. 5. Yeah. Okay, so this is a this is a traditional desktop GIS. Does everyone know what GIS is? No one? Geographic Information System in SIG in Spanish. Basically, this is a shapefile, which, as you can see, is a collection of polygons. This, in fact, is Barcelona, which is not considered to be very interesting for farming purposes. So it's just basically one giant polygon. There you can see that. Actually, that isn't Barcelona. Sorry. Where's Barcelona? There's Barcelona. It's the Puerto Olímpico. Right. So there's Barcelona. So click on that, and you can see some various attributes. And ZU. See the US there, so that's Zona Urbana. So then coming along here, just to show a little bit more, these are the, using someone else's laptop, it sucks. Right, so these are the artichoke fields. When you go down to the airport, you've never seen those fields. Best artichokes in Spain apparently. Anyway, so you can see this, as you go into more and more rural areas, the fields get more and more complex. And some of these, around Barcelona, they're quite sort of straight lines, but once you get into the Pyrenees, you can be absolutely incredible shapes, and thousands of points make these things up. So basically, we had to get all of these shapes into a database so that we could serve them up somehow to the farmers. So going back to, okay, so that's what we're just looking at, a shape file. So it's made up of 3 main files that have to be there: the shape, which is the geometry, the DBF, which is the attributes linked to it. Bit of a problem there, limited to 2 gigabytes. This is a big problem actually, because geographical data tends to be immense. You think of satellite images and things like that, you know, terabytes a day streaming down, so that's proven to be a real problem. There are ways around that. And the one at the bottom, PRJ, is projection information, because when you're walking around with your mobile phone using a GPS, it's latitude and longitude, which is obviously anywhere on the Earth, and it's got a code 4326. But actually, for most geospatial work, detailed work, you have local coordinate systems, where you have what's called a geoid, which is kind of a model of the Earth that's more accurate to the place where you are, and that's usually meters, which allows you to measure areas and things like that very accurately. So that's pretty much for shapefiles, really. The company that started it was called Esri. You can see Esri, which is sort of the Microsoft of GIS, and the application I just showed is QGIS, which is the open source competitor to it, essentially. Esri were charging thousands of license fees for people to do the simplest of things, but it's very much the industry standard, so I don't like them very much, as you can probably gather, but it's another story. So that. How do we get this back? Right, so the solution to who uses Postgres. Yeah. Okay, so who uses PostGIS? Ooh, more than I expected. Get it?
Not using, just installing.
Okay, so the solution for one of these awful shapefiles was to use a library called shape2pgsql, which we just write a little shell script which just dumped all 60 million straight into one database. And then I should point out this could be done in Python as well using the Fiona library, but I didn't. But there are, in the geospatial world, Python is very, very popular. But both QGIS, which I showed, and ArcGIS have Python as the main scripting language. So in the geo world, Python is popular, so that's a good thing. So basically what PostGIS is it's an extension that allows spatial data types to be handled like any other database object, and indexed and queried, and etc. etc. So PostGIS adds support for vector, raster, which is obviously satellite images, vector, which we've just seen, and topology, and it's ever growing. There are hundreds of functions. It's built on top of GEOS, which is a C++ port of a library called Java Topology Suite, and that's the library that allows you to do intersect shapes, containment, all these tests that are really important in JS, because we've got 60 million fields all around Spain, and you just want the one that you're interested in. You have to do an intersect test, and that has to happen quickly. Proj4j is a projection library that allows you to convert from latitude and longitude to something local, again for precision work. GDAL is utilities, and obviously it's a fully ASCII compliant RDBMS. I don't know, presumably lots of people work with MySQL too. MySQL?
Yes.
Yes. MySQL has spatial offerings, but until recently they kind of sucked, because you could only use MyISAM, which meant there was no support for transactions, so you couldn't replicate it, and it was generally just not as good as Postgres. If you're actually considering doing any serious geospatial work and you don't want to pay for an Oracle license, Postgres is the way to go. Index. The thing that makes this fast is Postgres is plug and play. This is something called a generalized search tree. When you create an index with a spatial object, it automatically uses an R tree, which is essentially a two-dimensional extension of an E tree. The idea is you take these complex polygons, and rather than checking that your point intersects with, potentially 100,000 line strings, which is mathematically very expensive, what it does is it stores the bounding boxes. So you have T and U there, which is the bounding boxes of, say, imagine that there's really complicated polygons in here. So if I say, tell me all the geometries that are here, then it will very quickly go down to L before it starts to actually do any tests for containments or intersections. Now I was going to run a query to demonstrate this. The second query, so intersects, very important operation. The geom is the geom of in the database, the fields. This is setting the spatial reference system to latitude and longitude. That is the latitude and longitude of Barcelona. This gets a point, and this will then return one record, Barcelona. When we were doing it earlier, when we ran through it, it returned in what?
Without the indexing?
Yeah, with the index.
37 point whatever.
No, with the index.
With the index, 0.57
milliseconds. Right. Take the index off, 36 milliseconds. And that's just with 60,000. I had a toy database which has 60,000 rather than 60 million. I work on data sets in the UK which go up to 1 billion, and it still returns in, a query like this will still return in sub-seconds, which is kind of incredible, really. So that's one of the things that PyBCN gives you. That was just to show that you can combine a sort of a more normal SQL query group by, this is agricultural use, some of the areas. This was to show you that the different types of classification which would correspond to the colours in that shapefile. Not terribly interesting, but the point is that with geometries you can do these interesting combinations of geometric and normal SQL queries, group bys and things on other attributes. So like I said, just give me all of the zona urbanas, or give me all the huertos, or give me all the forests, or whatever. There's millions more. There's millions of, hundreds actually, I'm exaggerating. I do like Postgres, but maybe not that much. There's hundreds of other functions in there that allow you all sorts of things, 3 dimensions, you can buffer things, you can shrink things, you can invert things, you can simplify geometries, you can convert them to GeoJSON, which is what we're coming to next. So, how do we get this stuff out and into the farmer's browser? I put the link here to the PyBCN reference frameworks to see that. There are literally hundreds of functions and growing all the time. That is pretty much, if you write select geom from, that's what the console will return you. Not very human readable, not very easy to deal with. GeoJSON has become the de facto interchange standard. Obviously, everyone uses JavaScript, everyone likes JSON, it works very well, so it's just another way of encoding geographic information inside a normal JSON packet of properties, essentially. That's a line string. It's a line string, it's got one bracket, and then the points are separated by, what's things? Right brackets, square brackets, and an array. The next page I've got a polygon. So this has got 3 at the beginning. So this is an outer ring, and this is an inner ring. Not terribly exciting, but there you go. That's how a polygon is encoded in GeoJSON. This is a query I wrote, which I was going to demonstrate, which is why we don't want to use this, but we want to use GeoDjango instead. This actually turns these 2 points into GeoJSON using some really ugly SQL. If anyone's using Postgres in 9.4 and 9.5, we're proper JSON creating objects which get away with all of this nastiness, but for 9.3 and below you have to do this. So array, ag, array to JSON. This is a way of bundling up loads of geometries inside a square bracket into an array, and then you have to cast this STS GeoJSON, selects a geometry and turns it into that. And then this puts all of this, just to put a CRS equals 4326 on it. Finally, turn the whole line into a feature correction, a row, and pump it out. So, I think you'll agree that's not the friendliest kind of query to be sending down the line. So, at this point, I'm going to pass it over to Dom, who's going to explain how we did it nicely.
I'm going to explain what GeoDjango is. How many of you have used Django or something different? Okay. So basically, GeoDjango is a binding for using the PostGIS functions using the Django framework. It's intended to build GIS web applications with maps and stuff like that. And the thing is that it's easy to use and avoids using the complex queries you saw when John was talking. So, if you have used Django, normally you define a model which will be reflected in the database. But here we are using the GeoDjango library, which is this one. If you look at this line, this field is the geometry field. Concretely, it's a polygon field. We can have different types of geometries, like polygons, multi-polygons, line strings, and things like that. And when using models which are linked to GeoDjango, we use this custom manager to interact with the database. Basically, for this example, we have used three functions, which are intersections from polygon to polygon to see where one polygon touches the other one, converting the geometry property to GeoJSON like this, and the last one is using geometry to get the area of the different points. And this is a little tricky, and I will explain it later. So, one important thing using GeoDjango is when you need to serialize this data. This is the geometry, and you need to serialize it to something more readable for us, like the standard GeoJSON output. And to do so, we will be using the vector formats library, which is the first line on the code. What we will be doing here basically is get this wrapper class, and we are telling that the geometry in the model is called geometry, and we can also specify some properties to output to this representation like this. Then basically we decode the different database result instances from Django, and then all of this information is encoded again to see each representation with GeoJSON. Basically, is that. Yes. Well, some code examples. The main use we have done in Agroptima is to see the different fields on the map, and to do so, we have used a function where we send a bounding box, which basically is the screen that you see on the map. We send different coordinates, which are the corners of the square. We create a polygon. In fact, it's a square, more or less, well, rectangle. And then, well, we create this polygon using the library from the Geo library. And then here it comes the magic. Basically, we search in our database, which is the line 34, using this lookup function from Django, and we are passing the polygon, which is the bounding box. Then this query set will return us all the fields containing or touching this bounding box. And then simply we serialize it with, it's the same as the example from before, and we output the data in GeoJSON format. What I told you about the area is that if we are using the coordinate reference systems 4326, which is basically what Google Maps uses, for instance. And if you are working with this, the area is not in square meters or something similar. It's represented by square degrees, and this is shit. And for example, if you want to convert it to square meters, the more straightforward way of doing it will be to change these coordinate reference systems to have the area in the units that you want. But if these coordinate reference systems are spread over the wall with different zones, depending on the country or the zone on the Earth. But we use globally, so we need to search a way to get square meters, and without changing this coordinate reference system, because you don't know, for example, in the backend, if you are working, if they are sending you a polygon from Europe or from America or South America or Africa, and changing the coordinate reference system can throw an error. So luckily for us, PostGIS has a library inside of it, and uses a field type which is geography, which we are casting this, that uses the representation of the Earth as a sphere, so it's very accurate, and basically we are using this to get the square meters with the geography tag, and this solves us a lot of headaches. And well, basically we're doing basically are passing this the raw SQL function here. Given a geometry, I simply get the JSON, I inject it in the raw SQL, and I get I use the function stArea, setting the coordinate reference system at the 4326. Sorry. And that's it. And it was the tricky part of our system implementation. So it's good to know. Okay. Now I'm going to show you basically a working example. So basically this is the platform the farmers are using. Okay, for example, this.
Can you change the inventory?
Yes.
It would show up better for that anyway.
Yes. Well, these are the different polygons loaded by this bounding box, which will be on this screen.
And you zoom out so we can see more.
Yes.
Can you change the mapping backdrop?
Yes.
It's easier to see.
What do you want?
I don't know, something that's not satellite.
It's
Nothing.
It looks better on.
internet goes here, but it's faster than that.
We crashed the server.
Yeah. Well, basically, this request is
Response.
yes. Basically, after sending these coordinates coordinates, which are basically the bounding box. We are receiving all the polygons, which are each polygon are a feature, and we are drawing it on the map. So maybe this is how it looks. Each representation. These are the coordinates of the polygon. As you can see, it's a lot of data for each feature. And well, that's almost it. I can also draw polygon, for instance. I can so after drawing this polygon, we send the geometry of this polygon to the backend, and it sends us these 5 features, which are the ones intersecting with this polygon, and this is the area in square meters, which is the function that I showed you before. And yes. Well, basically, it's not seen. Basically, these 5 rows here are the intersecting polygons intersecting with the micro polygon, and basically that's it. This was our implementation, and if you have questions or you can. Yes.
First one, yeah. How often your data is changing?
Top secret.
No, we can simplify question. Are users able to change the data?
Okay,
Yes.
so basically the official fields, I'm actually not allowed to say where they come from, but they change once a year.
Once a
That's
year.
applied to us, yeah.
And user can
users
edit.
are allowed to change them, yeah. So if the farmer buys another field, or he
Okay.
can go on and
But the
like,
user,
mark it up.
if I got this polygon and change it like this, you can change the shape of the polygon, and then I can send it again and put whatever, and it save it with
Then the question, how long it take to insert into the big database this new polygon? Because you need to rebuild index, right?
What we do, I can answer this.
Okay.
It's worse than you can possibly imagine. Without telling you where the data comes from, it's Windows only on a hard disk, and we have to basically take it off into shape files, pass all of the shape files, put them in Postgres, and rebuild it. It takes ages.
And you're rebuilding index from entire.
And then what we do is we actually we do it offline basically, and then we switch over. Yeah, actually building the index on, this is quite an interesting question. So you've seen the kind of complexity of the fields.
That's
60
my
million.
question.
It actually runs in about 2 hours. The actual create index option, and I've done like 500 million rows takes 8-10 hours, whatever, depending on the complexity. It's quite an impressively efficient operation.
And when you're inserting, am I right that you're rebuilding those zones? So you're rebuilding the part of the index?
Yeah, our trees aren't known to be particularly great for dealing with lots of inserts. You get dead rows when you do inserts and deletes in Postgres. You get rows that are marked as dead, but they're not actually cleaned out. And sometimes you get databases bloat massively, and you run an operation called analyze full? No. Repair? I can't remember. Anyway, it rebuilds it, and I've seen databases go from 120 gigs to sort of 80 just by reclaiming the space. The problem with that is, of course, it's locked while it's doing that. So this isn't doing this once a year is fine, but actually, if you had something where there were lots of inserts and deletes happening all the time, you would end up with a lot of fragmentation. You'd have to come up with some strategy for doing that. Postgres has a vacuum function, which is kind of this weird thing that runs in the background and analyzes tables and reclaims space if it can. But that's a good question. I think that is.
Thank you for answering.
Yep.
But from the API,
that's a problem.
doing
Vacuum full, sorry.
Little changes like that, usually it's very fast.
Vacuum full, that's the command. But that locks it, so use that with great caution.
You're saying that from the front end it looks fast. Is it rebuilding the index in real time, or you're just showing it on the front end and rebuilding it on the back end somewhere? Like, I mean, in foreground. Sorry, not in the back end. Foreground.
Are you talking about the index of the
Yeah, when you're moving it,
yes.
basically on the front end you're showing it like this. But if I will search for this field, let's say, or the intersection of this field.
Oh no, it's very quick.
Yes.
Yeah, once the index built, it's milliseconds.
They are not
In real
creating a
time.
new polygon there. It's just for the user to see. So you are not saving that in the database.
Yeah.
Well,
You're not saving.
No,
it.
it's just
That's-
pulling out.
That was, yeah.
The vast majority of the time is getting the GeoJSON down the wire. The actual Postgres query happens in milliseconds, and then the guy's sitting in the field on his, old 3G connection waiting for it. There are compression methods which we haven't put on yet for JSON, but that would be the next step. We tried to simplify the geometries, but it led to too many gaps, and farmers didn't like that. What's happened to my bit of field? So, we're stuck with the full payload.
No other questions? Can I fire one more?
Yeah, sure, yeah.
After you.
Who can sign up and create a new area? We can create a new area in any part of the world, or
With the area function, yes, you can work with Polygon from all over the world. It's no problem.
I need any accreditation to create an account in this system, or
Are you talking about the Agroptima?
yeah.
It's free to sign up.
You have a 15 trial
trialing.
trial time,
Plan.
and you can subscribe to it and get its functionalities. Have other questions I
Yeah,
can
maybe
explain
questions.
to you later.
Yeah. I noticed that you're using Leaflet as a map engine,
Yeah.
and you're using Mapbox as a map source.
Yes, for the tiles, yeah.
Yeah.
But we can change the map source if you want.
You have different.
We have a few. We actually started with Google, and
It was not good enough
Google?
for some places.
Google's fantastic if you're in San Francisco, New York, or London, right? And it's 3D and it was done yesterday. This farmer's going, I built a shed 10 years ago, it's not here. Problem. So we went to Mapbox, which is generally more up to date, but we had discovered problems there as well. There was a section that was shifted 10 meters in, was it Aragon?
Yes.
They messed up the processing of it. So, and that farmer said, "Where's my field? Moved 10 meters over there." So in the end, we thought, "Screw it. We'll just allow them to choose, and they can choose the one that works best for them." But defaults to Mapbox, right?
And in some fields, you have a big cloud covering all the area, so farmers are like, "Why I need to see this?"
Yeah. I mean,
That's why we have different imagery providers.
basically, there's no money in providing free tile sets. So at the end of the day, if you want really up-to-date stuff, you have to pay for it.
Yes.
I mean, there are microsamplers going up now. There's something in Planet Labs you might have heard of. Somebody's just going to put up these like 80 tiny little ones, and it does repeat imagery of the Earth every single day, and they're building that as for agricultural analysis and all sorts of other things that require, high spatial temporal repeat data. But they're not selling it in tiles. And I've done this, I can tell you, just for the UK, you're talking, if you build a tile server with various zoom levels, you're talking about 1 trillion just to cover the UK, which is tiny. So imagine, what the hell Google's got. Many, many trillions and many, many megabytes. It's a pain in the ass, and everyone wants it free and yesterday. So I can understand why. That's my perspective on it. But the Mapbox stuff has been okay, hasn't it?
For most cases, yes.
Yeah. And yeah.
No more questions?
Thank you.
Well, thanks a lot for coming. See you.